There are two types of programming languages: compiled languages and interpreted languages. Compiled languages, like C++ and Go, take the program code and transform it into files containing the instructions to execute in binary or assembly form. This process of transformation is called compilation. The compiler produces binaries that targets a specific CPU architecture and are optimized to run efficiently on that CPU architecture. On the flip side, we have interpreted languages. Instead of pre-compiling the program code into binaries, interpreted languages have an interpreter that translates each line of program code into binary code as that line is executed. The benefit of this approach is portability. You can run the same program code on many different CPU architectures without having to do any ahead-of-time compilation that targets a particular CPU. However, compiled languages have a performance advantage over interpreted languages. There's a third class of languages. This class covers languages that are compiled to a portable intermediate language, usually known as bytecode, and then interpreted. This fixes a couple of issues. First, you now have a compiler that can do things like type checking and code optimizations. Second, the bytecode is compiled only once, and because it's close to machine code, the effort to go from bytecode to machine code is much lower. And third, the bytecode is portable between different CPU architectures. This third style is the approach Java takes. The bytecode is stored in .class files, and the JVM interprets and executes it. However, the performance of interpreted bytecode still lags behind the performance of precompiled binary code. So in 1999, the JIT compiler was introduced and added to Sun's Hotspot JVM. The function of the JIT compiler is that during runtime, it identifies the parts of the application where the most time is spent executing bytecode, commonly known as hotspots, and then compiles the bytecode dynamically into machine code so that the program can run faster. The code is compiled just before execution, hence the name just in time, and is cached for future runs in the code cache. In this module, we'll talk about different types of JIT compilers in Java and how to choose the compilation mode. Then we'll look at the tuning flags for JIT compilation and what their effects are. Afterwards, we'll pivot to a detailed discussion of Java garbage collection. We'll discuss the different types of garbage collectors, how to monitor and measure garbage collection performance, and how to select and tune your garbage collector. In the Hotspot JVM, there are two JIT compilers: Compiler 1, commonly known as the C1 compiler or the client compiler, and Compiler 2, commonly known as the C2 compiler or server compiler. The C1 compiler is intended to be used by client applications, so for that reason it's optimized for startup performance. This means that it tries to find hot methods pretty early on, produces some basic, relatively unintrusive optimizations, and then compiles the method's bytecode to machine code. The C2 compiler is intended for use by server applications. The C2 compiler waits for a longer period of time before deciding to compile a hot method. This gives the compiler more time to learn about the method's execution pattern so that it can infer and apply more aggressive optimizations. As a result, methods compiled with C2 are generally faster than methods compiled with C1. However, because the C1 starts earlier than C2, an application running with the C1 compiler will be faster earlier on in its lifecycle before the C2 catches up and overtakes it. Therefore, if an application is short-lived or sensitive to startup times, then the C1 compiler is actually a better choice for it. But what if you could combine the two? What if you could have an application start running, and then after some runs, the C1 compiler picks up a method and optimizes it to get the intermediate performance benefit. And then at a later time, after some more runs, the method is re-optimized with the C2 compiler to get the faster machine code. This is exactly what the tiered compilation does. Tiered compilation is a compilation mode that was introduced in Java 7. And in tiered compilation, hot methods are first compiled with C1, and then as they get hotter, they are recompiled with C2. Although tiered compilation was introduced in Java 7, it wasn't until Java 8 that it became the default JIT compilation mode in the Hotspot JVM. The actual mechanism of tiered compilation is a bit complex, so I'll present a simplified version of it here. In tiered compilation, there are 5 execution levels. In level 0, the code is run in pure interpreted mode. In level 1, hot methods are compiled using the C1 compiler, and no further profiling is done. In level 2, hot methods are compiled using the C1 compiler, and there is some limited profiling being done. In level 3, methods are compiled using the C1 compiler with full profiling being done, and in level 4, methods are compiled using the C2 compiler. Profiling is needed for the C2 compiler to be able to infer the advanced optimizations that help it produce really high performance code. The normal path for a hot method is that it runs in level 0 interpreted mode, and then, if it meets the threshold for compilation, it's queued up for the C1 compiler and compiled at level 3 with full profiling so that it can later be moved up to the C2 compiler once it meets the requirements for level 4 execution. There are alternative compilation paths that use the other levels in edge cases, like the method being too trivial for C2 compilation, or one of the compilers being overloaded. The primary activity in compilation-based JVM tuning is choosing your compilation mode. This choice hinges on the type and nature of application you're executing. In general, because tiered compilation combines the best of server and client compilers, it should be your first choice. But there are situations where using just the client C1 compiler or the server C2 compiler could result in better performance. If you're developing a server app, then you should be choosing between the server compilation mode or the tiered compilation mode. For server applications, tiered compilation should perform better because you get the benefits of having C1 compile your hot methods in level 2 or 3 and provide some performance benefits before C2 compilation kicks in, whereas you wouldn't have that in plain server mode. However, it's still worth testing and benchmarking both compilation modes to see which works better for your application and workload. I've heard of a company that upgraded from Java 7 to Java 8, and after the upgrade, they noticed a drop in the performance of one of their applications. They spent a lot of time troubleshooting the performance decrease before realizing that the issue was that the Java 7 JRE they were initially using defaulted to the server compilation mode, while the Java 8 JRE defaults to the tiered compilation mode. As soon as they switched their Java 8 JRE to using server mode, their performance issue was fixed. So I would recommend checking the performance of your app with both compilation modes. The method for directing a JVM to strictly use the server or client compiler for JIT compilation has changed over time. In older versions of the Java runtime environment, you could do so by passing the -server or the -client flag as a Java command line option. But this has been changed since Java 8, and these flags are now largely ignored by the runtime. In Java 8, the simplest way to run in pure C1, that is client mode, is to set the tiered stop at level flag to 1. This setting keeps tiered compilation turned on, but caps the compilation level at level 1, leaving only 2 compilation levels. Level 0, which is the interpreted mode, and level 1, which is the C1 compiled mode, with no additional profiling overhead. To run in pure C2 compilation mode, you need to turn off tiered compilation. This results in the simple compilation policy being activated instead of the advanced compilation policy. With the simple compilation policy, hot methods are compiled just once at the highest compilation level, which by default is the C2 compiler level. The definition of what a hot method is quite complex and changes frequently between JDK updates. So again, I'm going to present to you a simplified version of it. The definition is primarily based on the value of 2 counters, the method invocation counter and the backEdge counter. The method invocation counter simply counts the number of times the method has been called, while the backEdge counter counts the number of times any loops in a method have branched back. This branch back count is effectively the number of times a loop has completed execution, either because it reached the end of the loop itself or because it executed a branching statement like continue. In tiered compilation mode, for an interpreted method to get selected for compilation by the C1 compiler in level 3, the following conditions must be met. The invocation count either has to be higher than the tier 3 invocation threshold, or the invocation counts must be higher than the minimum invocation threshold, and the sum of the invocation count and backEdge count is higher than the tier 3 compile threshold. By default, the tier 3 invocation threshold is set to 200, and the tier 3 compile threshold is set to 2000. For a method running in level 3 to be selected for level 4, which is the C2 compiler, the same condition has to be met, but with higher thresholds. Here the tier 4 invocation threshold is set by default to 5000, and the tier 4 compile threshold is set to 15,000. You could lower the threshold for level 4 compilation by passing in the appropriate command line flags to do so, but at the time of this recording, modifying the tier 4 invocation or compile threshold is not commonplace. Lowering the compilation threshold is much more common when plain server mode compilation is used. In this mode, the condition for compilation can be simplified as the sum of the invocation and backEdge counter must be above the compile threshold, and by default, the compile threshold is set to 10,000. A popular recommendation in performance cycles is to lower the compile threshold in server mode to 8,000. This can result in better performance for 2 reasons. One is that compilation happens a little earlier in the application lifecycle, which helps you get faster code running a little bit sooner, And the second reason is that there may be certain methods which are frequently called but would never get compiled because they wouldn't meet the 10,000 invocations bar. With the lower threshold, these methods will now get compiled. Like any other recommendation, you should test whether this works for your application and hardware before making a final decision. The last thing we'll look at when it comes to JIT compilation is the size of the code cache. The code cache is an area of native memory where compiled code is stored for future execution. If the code cache gets filled up, normal compilations will be done, and hot methods may continue to run in the slower interpreted or C1 compiled mode. This should rarely happen though, as Java 8 typically reserves 50 megabytes for the code cache when tiered compilation is off, and 250 megabytes if tiered compilation is on. This should be more than enough for most applications. However, if a Java application does run out of code cache space, the JVM will print out a warning message that you can go back into your logs or command prompt to examine. You can also take a look at the code cache capacity using Java Mission Control or other monitoring tools. If you do find that you need to increase your code cache size, you can do so by setting the JVM flag Reserved Code Cache Size. In Java 9 and above, the code cache has been segmented into 3 areas. An area for JVM internal non-method code, an area for code that's being profiled, and an area for fully optimized non-profiled code. This segmentation allows the JVM to optimize its cache cleanup process, as it never needs to clean up the JVM non-method code. It also allows for better management of the JVM's memory footprint, as you can now reduce the size of the profiled code section, for example, as it only contains methods that don't need to stick around for very long. To set the sizes of the 3 code cache areas, use the non-end method code heap size flag for the internal JVM code, the profiled code heap size for the lightly optimized code, and the non-profiled code heap size for the fully optimized code. Note that in Java 9 and above, if you use the old reserved code cache size flag to manage the size of the code cache instead of using one of these newer flags, the JVM will turn off the segmented code cache feature and return to treating the code cache as a single entity. Garbage collection is the mechanism by which the JVM reclaims memory on behalf of the application when it's no longer needed. At a high level, it consists of finding objects that are no longer in use, freeing the memory associated with these objects, and occasionally compacting the heap to prevent memory fragmentation. The garbage collector performs its work using one or more threads. But in order to do the job of tracking down object references and moving objects around in memory, it needs to make sure that the application threads are not currently using the objects, because if, for example, an application thread is using an object, and the memory location of the object changes due to GC, then bad and unpredictable things could happen. This is why garbage collection must pause all application threads while running. These pauses are sometimes called stop-the-world pauses, and the minimization of them is a primary concern of GC tuning, as they can have a huge impact on the performance of a Java application. There are 4 main garbage collectors available in current JVMs. They are the serial collector, the parallel collector, which is also known as the throughput collector, the concurrent mark sweep collector, or CMS collector, and the garbage first garbage collector, or G1GC. The standard garbage collection architecture today is generational garbage collection, and all 4 aforementioned collectors are generational garbage collectors. Generational garbage collectors divide the heap into 2 areas, the young generation area and the old generation or tenured area. The young generation itself is split into 2 logical areas, Eden space, also known as the allocation space, and the survivor space. Finally, the survivor space is also split up into 2, survivor space 0, S0, and survivor space 1, S1. Objects are created in the Eden space of the young generation area, and when Eden fills up, a minor garbage collection takes place. Minor GCs are optimized with the assumption that objects have a high mortality rate and are typically very fast. During the minor GC, objects are first checked to see if they are still reachable or not, and then marked accordingly. Then reachable objects in Eden have their age incremented and are then copied to a designated survivor space. Objects in the other survivor space also have their age incremented, and if they reach a certain threshold, known as the tenured age, they get promoted to the tenured generation. But if they are under the tenured age, then they also get copied to the currently designated survivor space. Then both Eden and the other survivor space are cleared, freeing the memory and compacting the space at the same time. The process is the same on the next minor GC run, but the survivor spaces switch roles and the empty survivor space becomes the designated survivor space. Referenced objects are copied to this survivor space or tenured to the old generation, while Eden and the other survivor space get cleared after the GC, and it goes back and forth from there. Eventually, the old generation also gets filled up and must be garbage collected. This is called a major or full garbage collection, and it usually takes up more time because the search space and number of objects is higher. This is where GC algorithms have their biggest differences. Basic collectors will stop all application threads, mark the unreachable objects, free their memory, compact the heap, and then resume the application threads. Whereas more advanced collectors are able to scan for unreachable objects even when the application threads are still running, and only pause all application threads to free the memory and compact the heap. These collectors are known as concurrent collectors, mostly concurrent collectors, or low-pause collectors. The concurrent mark sweep and G1GC collectors are concurrent collectors, while the parallel collector is a basic collector. The choice of collector depends on a number of factors, such as the size of the heap and the amount of live data your application uses, the number and speed of available processors, and whether or not your application is an online interactive application with low pause requirements. The serial collector is the simplest garbage collector available in Hotspot. It uses only one thread to process the heap, both for minor and major collections, and it'll stop all application threads while doing so. To enable the serial collector, use the +userialgc flag. If your application will run on systems with only one processor or virtual processor, and there are no pause time requirements, or if you're running a lot of small JVMs on a single machine, then you should use the serial collector. Another use case for the serial collector is if you have a small live set of data up to approximately 100 megabytes. In this case, using multiple threads to process the heap may not produce much of an advantage, especially considering the inter-thread communication overhead involved. For machines with multiple cores or 64-bit JVMs, the parallel collector is the default collector if you're running Java 7 or 8. The parallel collector uses multiple threads for minor and major collections, and fully stops all application threads for both collections. This means the use of the parallel collector can result in long pause times of sometimes over a second, but overall, application throughput should be higher with the parallel collector than with the low pause collector. Therefore, if you're running a non-interactive batch application, where overall application performance is more important than low pause times, then you should go with this collector. If you're running Java 9 or later, then to enable the parallel collector, you would set the +useparalegc flag. For Java 7 or 8, you shouldn't need this flag as it's the default. The CMS collector was the first concurrent collector to be introduced to the Hotspot JVM. As a concurrent collector, it's able to trace reachable objects and clean up unreachable ones all while live application threads are still running, allowing it to achieve short GC pauses. However, since the GC threads run concurrently with application threads, the GC threads may compete with application threads for CPU resources. Therefore, a CPU-bound application may see a reduction in application throughput when GC threads are running. To use the CMS collector, pass the +useconc_mark_sweep_gc flag to the JVM. However, you should note that G1GC, which is the newer JVM concurrent collector, has been pegged as a replacement for the CMS collector, and since Java 9, the CMS collector has been marked as deprecated and will eventually be removed from the JVM codebase. The garbage-first garbage collector, G1GC, is the replacement for the CMS collector, and is the default collector in Java 9 and above. It's designed for multiprocessor machines with large heaps, and it tries to achieve the best balance between latency and throughput. With G1GC, you can specify a goal for the maximum pause time you would want your application to encounter, and the collector will try to meet the requirement by trying to reclaim as much space as it can within the given constraints. G1GC is a mostly concurrent collector. G1GC threads mark unreachable objects concurrently while the application threads are running. This means that, like the CMS collector, overhead from the concurrent execution may affect application throughput. Therefore, G1GC should be used if you have an interactive application, application response time is more important than overall throughput, and there's a requirement to keep pause times short. To enable G1GC in Java 7 or 8, set the +useg1gc flag. For Java 9 and up, this is the default already, and you shouldn't need to set this flag. Note that these are general recommendations. If you still don't achieve the performance you want, then you should try tuning your collector. And if you still can't reach your performance goals, then you can try using a different collector. One interesting option for an alternative garbage collector is the Shenandoah garbage collector. As of the time of this recording, the Shenandoah collector is not considered to be production ready, but the promise of Shenandoah is that it takes the next step beyond G1GC. While G1GC does a concurrent mark but the moving of objects takes place during the stop the world phase, Shenandoah is able to do both the marking and moving concurrently, without stopping the application threads, bringing garbage collection closer to being a fully concurrent process. Based on different benchmarks, Shenandoah is able to achieve pause times that are on average 10 times smaller than G1GC pause times, while only decreasing throughput by 10%. I won't cover Shenandoah in this course as it's still experimental at this point, but it's one to keep an eye on. If you're trying to choose between two or more different garbage collectors, you need to be able to stack them up against each other. To do so, you would need the operational metrics of the garbage collectors you're testing, and the best way of acquiring these metrics is by turning on GC logging. The GC log contains information such as when collections were run, how long they lasted, what the pause times were, how much memory was reclaimed, how many objects were promoted to the old generation, and more. To produce the log, you need to pass a flag to tell the JVM what to print and where to print it to. In Java 7 and 8, the relevant flags are the print GC details flag, which tells the JVM to print statistics on GC events and how much memory is reclaimed by garbage collection, the print GC datestamps flag, which tells the JVM to print the absolute timestamp in the log statement instead of relative time, and the log GC flag, which gives a path to a file that the log will be written to. If the file path is not given, then the log will be written to standard out. In addition to the above flags, if you choose to have GC logging constantly turned on in production, which is generally a good thing to have, then you may want to use log file rotation. The following configuration tells the garbage collector to rotate log files, keeping the last 10 log files, with each file maxing out at 10 megabytes. In Java 9 and above, the flags for enabling GC logging have changed. The log column GC flag enables GC logging to standard out, and adding the file path redirects the output to the specified file. To enable log rotation, you can add the file size and file count options. And to add additional details to the GC log, like the liveliness info, the heap info, the tenoring age distribution, and more, add an asterisk to the GC portion of the flag. If you have a Java 9 and higher JVM that's already running, you can enable GC logging dynamically using jcmd's vm.log command. Once the log is produced, you can open it with a text editor and have a look at the contents. Here's an example of a GC log produced by the G1GC collector in the Java 11 EnergyMart JVM. Here, you can see some interesting information like the start of a young collection, the movement of objects from Eden to Survivor Space and to the old generation, the pause times, the drop in memory usage after the GC run, and more. This particular log is in the unified logging format that was introduced in Java 9. In previous versions of Java, the format was specific to the garbage collector and JVM version, so the G1 collector running on Java 8 would have a different log format as the CMS collector. But with Java 9, a uniform logging framework was introduced so that all JVM components, including garbage collection, produce logs in a standard format, regardless of which collector is used. Now that you have the log file, you need to analyze it. There are a couple of options for doing so. One option is to analyze the log using manual tools like text editors and Excel spreadsheets. But that's a horribly tedious process unless you have the infrastructure already set up. Another option is to use a third-party program for the analysis. The two most popular third-party GC analysis tools are gceasy.io and GCViewer. To use GCeasy to analyze GC logs, navigate your browser to gceasy.io. On the home screen, you'll see the Upload GC log file option. Click the Browse button and select the file to upload, then click Analyze. GCeasy will then analyze the log file and present an analysis report to you. First up is a heap size report, which shows the amount of memory allocated for the different areas of the heap versus the max amount used at some point in time. Next, you'll be presented with the distribution of the pause times, and you can see the average and max pause time. You can also see the GC throughput right here. If you hover over the green question mark icon, it'll show you how it calculates the metric. Throughput is calculated as the percentage of application time spent processing real transactions versus doing GC activity. There's much more information presented in the report. There's the interactive graphs, where you can visualize GC duration or visualize the different heap areas before and after garbage collection. There's also some object stats available, which can show you things like the number of created bytes and how many of those bytes got promoted to the old generation, and what the object creation and promotion rate was. And there's also a memory leak detector. So this is the report for G1GC on Java 11. If I want to compare this performance versus G1GC on Java 8, or versus the CMS or parallel collectors, I can open multiple browser tabs and upload the different files. Now I can stack these garbage collectors against each other and judge them based on memory footprint, throughput, and latency. Now this wasn't a perfect test because the test durations are slightly different. But for this particular application running on my local PC hardware with randomly generated load test traffic, I can see that in terms of memory footprint, CMS wins with the least amount of peak memory usage, followed by the parallel collector, which just slightly edges out the Java 11 G1GC collector. The Java 11 G1GC collector is best for throughput, followed by its Java 8 counterpart, and then by the CMS collector. But CMS produces the smallest average pause times, followed by the G1 collectors. So now that we are able to measure GC performance, let's talk about tuning garbage collection. The first step in garbage collection tuning is tuning the size of the heap. This is because if the heap is too small, then too many GCs will occur in order to reclaim memory, which could reduce the overall application throughput. And if the heap is too big, there will be fewer GCs, but those GCs would take a long time, and your response time metrics would take a hit. The parallel collectors are especially vulnerable to this problem. So if you're going to need a large heap and low pause times, then you should try the G1GC collector. The size of the heap is controlled by two flags, an initial value specified with the MS flag and a maximum value specified with the MX flag. Having an initial and maximum size for the heap allows the JVM to auto-tune the heap size depending on the workload. If the JVM is experiencing memory pressure and observes that it's doing too much GC, it will continually increase the heap until the memory pressure dissipates, or until the heap hits its maximum size. And if the memory pressure is low, the JVM can also decide to reduce pause times by shrinking the heap size. This process is known as adaptive sizing, and it adjusts not only the overall size of the heap, but also the size and ratio of the young and old generations. If you've taken time to finely tune your application's GC behavior and sizes, you may choose to turn off adaptive sizing. This can save the JVM the small period of time that it takes to do the calculation for what the heap size should be. You can do so by setting the flag Use Adaptive Size Policy to false. Also, setting the initial heap size to the same value as the max heap size, or the initial new generation size to the same value as the max new generation size, effectively turns off part of the adaptive sizing behavior. A strongly recommended guideline for setting the max heap size is that the max heap size should not exceed the amount of physical memory on the machine. And if you have multiple JVMs running, the sum of max heap sizes should not exceed the machine's physical memory. A more general recommendation for setting max heap size is that it should be set so that the heap is about 30% occupied after a full GC. To calculate this, you can look at the GC log for an entry where a full GC takes place and observe how much memory is used when the GC completes. You can also run the application until it has reached a steady state and then force a full GC with JConsole or JCMD. If adaptive sizing is turned on, then you can use the max GC pause millis flag to tune GC behavior. This flag sets a target for the maximum GC pause time. When used with a parallel collector, the JVM will adjust the size of the young and old generations in order to try and meet the goal. It will then adjust the size of the heap so that the time spent in GC does not exceed a certain value, which by default is 1%. One of the goals of G1GC is that it will need minimal tuning. So in G1GC, the max GC pause millis flag goes beyond adjusting the heap sizes to include starting background processing sooner, changing the tenoring threshold, and adjusting the number of old regions processed, all in order to meet the pause time goals. In G1GC, the default value of the flag is 200 milliseconds. While you may be tempted to set this to something really small like 20 milliseconds, note that to try to achieve this, the collector will contract the young generation to a really small size and collect less of the old generation, which will eventually lead to a situation where there's too much garbage in the old collection and the system would have to perform a full GC, which is undesirable. Like the now deprecated CMS collector, G1GC is a concurrent collector. This means that some of the phases of the garbage collection process can be running concurrently with application threads. This can lead to a situation where the old generation runs out of memory while the collector is in the middle of the garbage collection process, since the application is still running and is producing garbage faster than it can be cleaned. This situation is known as either a concurrent failure mode, a promotion failure, or an evacuation failure, depending on when the failure occurs. If you see a lot of these failures in the GC logs, the solution is either to increase the size of the heap, start G1 background processing earlier, or speed up GC processing by using more background threads. To perform G1 background activities more frequently, you can reduce the threshold at which a G1 cycle is triggered. This is achieved by reducing the value of the initiating heap occupancy % flag. This flag is set to 45 by default. This means that a GC cycle is triggered when the heap becomes 45% filled. Reducing this value means that a GC would get triggered earlier and more often. But care should be taken that the value is not set to a number that's too low, which would result in GCs happening too frequently. To increase the number of background threads, use the conc GC threads flag. The default value for this flag is set to the value of parallel GC threads plus 2 divided by 4. As long as you have sufficient CPU available on the machine, you can increase this value without incurring any performance penalties. If tuning the size of the heap and tuning the collector doesn't work for you, then you can try another collector. And if you still aren't getting good results, then you need to look at tuning the application code itself.